Hello viewers, welcome to Unacademy YouTube channel. Myself Vetrivel, Unacademy Plus educator. Unacademy is the best for online coaching at present, right? It's the best plan for Karnataka CET 2021 aspirant. Those who are looking for KCET 2021, JEE and NEET, Unacademy is the best one at the moment, right? It's the topmost coaching and teaching platform in India. So comprehensive batch is live on Unacademy for complete syllabus preparation, right? You can have a 1 month plan or 6 month or 12-month plan, right? It is affordable price, right? And regular interval of self-analysis quizzes will be there, structured live courses and dedicated live doubt clearing session, batches for complete preparation, right? So everything single subscription for unlimited access. So use my code VetriLive, subscribe Unacademy so you can enjoy the learning, right? Today I am going to discuss fluid mechanics. In that we are going to restrict ourselves only to the concept of density, pressure and Pascal law, Archimedes principle. So based on this concept we are going to discuss today. So once again I welcome you all on Unacademy YouTube channel. Here let us see the basic first, right? See that the first question. Before moving into that, just I want to remind you, right? We all know pressure, right? Force acting per unit area, right? Newton per square meter, that's only Pascal, or Pascal is the unit. The pressure exerted by the atmosphere is called atmospheric pressure. We all know 1 atmospheric pressure equal 1.013 into 10 power 5 Pascal, right? So this atmospheric pressure at a depth, suppose the vessel the surface of water where atmospheric pressure, say suppose PO is acting. If I consider the point P at a distance depth D inside, what is the pressure at point P? Usually we know liquid exert an upthrust. Whenever a body immersed partially or wholly inside a fluid, it experiences an upward thrust, upward force. That's only buoyant force. Now, what is the pressure acting at a point, right, at a depth D from the top surface of water? Now, the total pressure acting at point P is atmospheric pressure plus the liquid pressure, right? That is H rho G, where H is height of this liquid column and rho density of the liquid, G we know acceleration due to gravity, right? So liquid exert pressure at a point in all the direction, right? The pressure, it will act along in all the direction, not on particular direction. That is why pressure is tensor quantity. It is not a scalar or vector. Pressure is a tensor because it acts at different direction, right? Then we all know density, right? Mass per unit volume. Remember, so density of the substance generally, right? Mass per unit volume we know. The density of the body or density of the substance. Here, relative density, the term you must know. Relative density is the ratio of density of the body to the density of water. Relative density, another name, specific gravity. Relative density or specific gravity is the ratio of density of substance by density of that same substance or body in, they will compare density of the body to the density of water at 4 degrees Celsius. The ratio of density of substance to the density of water at 4 degrees Celsius, because water has the highest density at 4 degrees Celsius. So relative density or specific gravity is the pure ratio, so no dimension, no unit. Relative density is the ratio of density of the substance to the density of water at 4 degrees Celsius, right? So we all know Pascal law, remember? So it states that if the gravity effect is neglected, the pressure at every point in a liquid in equilibrium of rest is same. If the pressure act at any one point, it is equally, right, undiminishedly distributed, right? For example, hydraulic lift and hydraulic brake, we know. Here buoyancy, we all know that if weight of the body equal to mg, here m equal, we know that density equal to mass per volume, from that mass equal volume into density, right? Weight, we know that mg, right? Weight is the force with which attract towards the earth. M place substitute, volume into density into g, right? This is laws of flotation. If weight of the body is greater than buoyant force, buoyancy, then the body will sink. If the weight of the body, buoyant force, if the weight of the body is less than the upthrust, that's only buoyancy or buoyant force, right? Weight of the body is less than the buoyant force, then the body will float on the surface. If the weight of the body is equal to buoyant force or upthrust, then it will partially float on the liquid, right? So have this idea, right? Let us move to the problem straight away now. Right now, let us see the first sum. So the first sum will go ahead now. Yes. Here is the first problem. See that the sphere of iron and lead having same mass are completely immersed in water. Density of lead is more than iron. See here, density of lead is more than iron. Apparent loss of weight W1 for iron sphere and W2 for lead sphere, the ratio is, see here clearly, right? The sphere of iron ball and lead, right? Same mass, that's only important. Both have same mass, are completely immersed inside a fluid, right? It is completely immersed inside a water. Density of lead is more than density of iron, right? So what is the apparent loss of water in W1 for iron and W2 for lead when both are immersed inside, right? So what is the apparent, whenever any object, when you immerse inside, there is a apparent loss in weight, right? So here question, the key point you need to understand properly, right? Then you will understand easily. First, Iron and lead same mass. Okay, then both as immersed in water. Density of lead is more than that of iron. What is density? We know density equal to mass per volume, right? Clear. So here mass per volume. How density related to volume? Density is inversely proportional to volume. See here, right? Density mass per volume. So density is inversely proportional to volume. Now here density is same for both. That is given clearly in the question. See, density of lead is more than that of iron, but here same mass, right? Mass is remain constant, same. That is why mass is 1. So 1 by V. Mass is same for both, same mass. Okay. Now density of lead by density of iron, right? That is how it relation. This I am writing. Density of lead by density of iron equal to volume inversely proportional. So volume of iron inversely proportional by volume of lead, right? So here what is condition given? Density of lead is greater than density of iron is given. This is condition given in the problem itself, right? Then okay, density of lead is more than density of iron is the given. Now that meaning volume of iron by volume of lead, right? It is greater than 1 because density of lead is greater than density of iron. So we can use even laws of flotation. Laws of flotation, as I said, right? W equal m into g. M is volume into density into g. W equal to mg. M is volume into density. So here use this laws of flotation. W1 equal weight of the lead equal, right? Okay, V iron into rho, right? Water, density of water into G. Similarly for this is first one for iron. Now let us go for lead sphere. W2 equal V lead density of water into G. Now these both divide, W1 by W2 divide now. W1 by W2 equaled, right? V volume of iron by volume of lead. What is that already? Volume of iron by volume of lead is greater than 1. So option D, see that. Option D is the correct answer. It is greater than 1. Yes. Let us go for next one. The pressure on a swimmer 20 meter below the surface of water at sea level is, we know atmospheric pressure at sea level is 760 mm of Hg. Here the question, see clearly, a swimmer on 20 meter below the surface of water, right? This is the surface of water, fully see that is the top, 20 meter height, see that a swimmer is 20 meter below the surface of water. Assume here he is swimming, right? Now height is given, height of the liquid level or swimmer 20 meter. What is density of water? We know the constant value. Density of water is SI unit 1000 kg per meter cube. Density of water. What is atmospheric pressure? PA or PO. Atmospheric pressure, we know constant value 1.013 into 10 power 5 Newton per meter square or Pascal, right? We know that density of water 1000 kg per meter cube. Atmospheric pressure we know. Here, see that the swimmer is swimming, right, 20 meter below. At this point, what is the pressure on the top surface? Atmospheric pressure is acting. This is depth H's. At this point, the pressure we know, total net pressure equal atmospheric pressure plus what is the pressure exerted by this liquid column? H rho G. Right? That's it. Now you can go ahead. P equal net pressure. Question is, what is the pressure below 20 meter height? So atmospheric pressure is given 1.031 into 10 power 5 into, right, PA atmospheric pressure plus H rho G. H is 20, rho density of water into G 9.8 or 10, you can go ahead, round value. Then you will get answer, right, 3.01 into 10 power 5 Pascal. That is nothing but 3 atm, because 1 atmosphere is 10 power 5 into, that is why it is 3 atmosphere. So option D is correct one. 3 atmospheric pressure is the correct answer. Right? This is pressure at a depth, right, inside the water. Immediately use this formula. P equal atmospheric pressure plus, right, liquid pressure H rho G or HdG. Yes, we'll go for the next sum. The next problem. Here it is. If the atmospheric pressure is PA, the pressure exerted by the atmosphere, then the pressure P at a depth H below the surface of the liquid density rho in open to atmosphere, that means open atmosphere is such that we discuss the two sum based on that formula. Atmospheric pressure PA, right, then the pressure P at a depth below the surface of the liquid. This is same what we discussed now. This is the liquid level, surface of the liquid at a point inside the liquid, at a point depth or height, depth D or H, you can take it. What is the pressure at this point? On the surface, atmospheric pressure is acting. This is the formula we know. Atmospheric pressure plus liquid pressure, right? H rho G. So this is the correct answer. Let us go to the next question. Right? Here it is. 3 liquids of equal masses are taken. See that properly first. 3 liquids of equal masses in 3 identical cubical vessels, right, A, B, C, are taken, equal masses. Their densities are rho A, rho B, rho C respectively. But density of A is less than B, B is less than C. The force exerted by the liquid on the base of the cubical vessel is, right? Yes, you know that in this case the pressure exerted will be, what is that? 3 vessel, see that 3 liquids of equal masses taken in 3 identical cubical vessel A, B, C. Density is given, but density of A is less than B, less than C. The force exerted by the liquid on the base of the cubical vessel. We all know the pressure exerted by the liquid on the base of the vessel, P equal H rho G, right? It always exerts equally in all the direction, right? So this is the same in all the vessel, because the first vessel, what we will get usually, MA equal to MB equal to MC, the mass, because 3 identical cuboid vessel, and force on A will be equal to force on B will be equal to force on C. liquid exert equal pressure in all direction, right? So whatever the shape of the vessel, so the same in all three vessel. C is the correct option, right? Yes. Let us go for the next question. By sucking through a straw, a student can reduce the pressure in his lungs to 750 millimeter of mercury level. Density of mercury is given. Using the straw, he can drink water from a glass up to the maximum depth of how much? Maximum depth they are asking, how much he can able to suck water. By sucking through straw, a student can reduce the pressure of his lungs 750 mm of Hg. What is the atmospheric pressure then? 760. That means, what is the pressure difference first? Right? The pressure difference between lungs and atmosphere, outside pressure and lungs when you are sucking, right? So the pressure difference between lungs and atmosphere, right? That is, atmospheric pressure is, we know, 760 mm of Hg minus, when he sucked, how much his pressure now he reduced? 750. So the pressure difference between lungs and atmosphere is 750 minus 760 minus 750, 10 millimeter of mercury level Hg, right? Okay, here that meaning, see, according to problem, H rho G, that means he is sucking water, that is equal to H rho G, while he is sucking, what is that? Mercury level, right? So this, both are equal, understand? So question is, by sucking straw, he reduced his lungs 750 mm of mercury level. When he drink water from the glass, up to what depth he can able to suck up? That's only, right? So we want to find only the height of here, water level, how much he can able to depth, how much he can able to suck, so that maximum depth will get. This is equal, write it, remaining all, see, mercury density by water density into, right, the height of the mercury level. That's it. Mercury density we know 13.6. Mercury density of water 1 gram per centimeter cube. Here all in centimeter given, CGS unit. If it is given SI unit, mean it will be 1000 kg per meter cube. It is given in CGS unit, so CGS unit density of water is 1 gram per centimeter cube by 1 into, what is this is? Weight, full level, let's say 1. So it is will be 13.6 centimeter. Option C is the correct one. Yes, let us go for the next one. See here, from the adjacent figure, the correct observation is, you see that figure, the size of the vessel, see, water level you see, the pressure on the bottom of the tank A is greater than at B. The pressure on the bottom of the tank A is similar at the bottom B. The pressure depends on the shape of the container. The pressure on the bottom A and B is the same. Yes. Now have a try now. Right? See that which option is the correct one from the adjacent figure. The correct observation is, which observation is correct? Have an idea now quickly. Right? Pressure from the adjacent figure, right? The pressure on the bottom of the vessel. All the option you see that eliminate, which is not at all suit here, right? You can eliminate it, then you can understand. See that we know that at any point inside the fluid, pressure will exert equally in all the direction, right? So the pressure on the bottom of A and B is the same. Even though the area of cross section differ, the pressure will be same at the bottom. So option B, D is correct, right? Okay. Let us go for the next one. Yes, you can see now clearly it is given a U-tube with both ends are open, right? Both sides are open to the atmosphere, so atmospheric pressure will exert. It is partially filled with water, oil, see partially up to here water, this dotted all oil, which is immiscible with the water, it won't mix it with the water, is poured into one side until it stands at the distance of 10 millimeter above the water level. That means from see above the water level, it is 10 mm above this water level, which is oil. Now, above the water level on the other side. Meanwhile, the water rises by 65 mm from its original level. The density of the oil is, you see here, original level 65 mm here, initial level of water here, right? Initial level, final level of water. When we pour oil, initially water will be here, initial level, right? Both sides it will be same. When we pour this one side oil, so it exerts pressure so that water level, this limb will go down, here it will rise. Here final water level. So see here, from this mean position 65 mm, water rises 65 mm this side. From here it rises 65 mm. Here this side it lowers 65 mm. The water level from final level, okay, 10 mm, it is oil is above that. That's only is given. Is poured on one side until it stands at a distance of 10 mm above the water. Now see that what is the question here they ask, right? Question, try to understand. What is the question? The density of the oil is, right? Here pressure on the both side are equal. Initially see that initial water when we poured, now when it is standing in equilibrium position, what happened? Pressure on both sides equal. So P1 equal to P2, right? Is a liquid is there, either oil or water. What is the pressure on a liquid column? We know H rho G, right? HdG. Here, suppose one side I am taking all oil. Height of the oil, density of the oil is equal to that side water I am taking. H rho G, water. Density of water, height of the water. We need to find what is density of oil, only keep this side. Remaining all take that side. G cancel it. So what will get now? It will go that side, height of the water into density of water by, right? It will come down height of the oil. That's it. So density of oil equal, see the height of water. Height of water 65 mm plus again, see from this position, this side 65, here 65 total, right? 65 plus 65 height of water, and density of water, we know density of water 1000 kg per meter cube by height of oil. Height of oil, you can see that from this starting position 65 plus 65 plus 10. See already water height will be 65 plus 65 plus mercury level height above difference is 10. So simplify this all, divide, simplify, you will get option D. 928 is the correct option. Yes. Very simple here. Even oil mixed in this, the pressure will be same on both the side. So use pressure formula, liquid pressure on our column. HdG or H rho G equal, either side equal, we can find density of oil. D is the correct option. Let us go for next question. A log of wood mass 120 kg. See that? A log of wood of mass 120 kg floats in water. The weight that can be put on the raft to make it just sink, its density of wood is given. Right? Which is the correct option. Here we know what is the volume of the wood. Volume will be mass per density. Density equal to mass per volume. Volume of the wood, mass per density. Mass is given, right? Density of the wood also given. Volume equal to mass per density. So you will get volume of the wood 0. Volume meter cube, 0.2 meter cube. Right. So now question is, see, the weight that can be put on the raft that make it just sing on the wood we are keeping. Let x be the weight that can be put on the log of wood. On the log of wood, what weight you are keeping? Right? Let x be the weight that can be put on the log of wood. So the weight of the body, is already log is 120 plus you are keeping additional on that, that is x, that weight, right? Weight equal to mg, m is 120 log weight plus x, we don't know, into mg, this is mass, w, weight equal m into g, right? So g is here 10 newton, take it, that's it. Now weight of the liquid displaced, how much it is going inside, that much volume of water will be displaced. So weight of the water displaced, right? The weight of the water displaced, right? Now the weight of water displaced, equal, see, m into g, right? M we can write mass, we can write volume into density into g, right? So it's given already, volume we got 0.2 here, 0.2 into density of water 1000, so 10 power 3 into g 10, that's it. Now the body will just sink if the liquid, right, if the weight of the body will be equal to the weight of the displaced liquid, right? So equate these both, right? Equate it now, that's only, if we equate it, find x, that's all. So we know that 120 plus x into 10 equal 0.2 into 10 power 3 into 10, that's all. Simplify from this, x you will get 80 kg. Here question is, on the wooden block, how much weight you will keep it so that it just to sink, right? So x equal to, you will get 80 kilogram is the correct option. Right, let us go for the next question. Here it is. Two solid pieces, one of steel and other is aluminium, when immersed completely in water have equal weight. When the solid pieces are weighed in air, what happens? When the solid piece is weighed in air, see, two solid pieces, one is steel, other is aluminium. When immersed completely in water, they have equal weight. But when solid pieces are weighed in air, now separately you can weigh it in the air, what happens? Aluminium piece will be weighed more, right? Keep in mind the density. Aluminium piece will weigh more, right? So a body floats in water with 1/3 of its volume above the surface of water. If it is placed in oil, it floats with half of the volume above the surface of the oil. Then the specific gravity of the oil is, right? Question is specific gravity of the oil. Now we know that specific gravity is the ratio of density of substance to the density of water at 4 degrees Celsius. Here, a body floats in water 1/3 of its volume above the surface. The remaining 2/3 will be inside. If it is placed in oil, half of its volume above and remaining half will be inside. What is the specific gravity of the oil? What is the weight of the body here? Right? The weight of the body equal weight of the water displaced, how much is immersed inside. Weight of the body is equal, according to Archimedes principle, whenever it is immersed, weight of the body is equal to weight of the water displaced. When I placed in water, it is water displaced. Suppose when I placed in oil, right, weight of oil displaced, that's all, right? Both cases given. First you are placing in water and then in there. Now see that both, it will be, what is the weight? Mg. We have condition given first. 2/3. See, 1/3 of its volume above the surface. That means remaining 2/3 will be inside. Volume into density into G. Right? V. Clear. So, yes. Now see. Yes. 2/3 will be inside the water, right? 1/3 is above mean. Then you can go ahead now. It will be how much portion is inside? 2/3. Its volume into density into G, right? That is same as equal to, we know that. What is the weight of the oil displaced is given half of them. See the question, right? Half of its volume above the surface of the oil. So, half of them volume into density into G. Here we need to find only density of the oil. Here it is density of water. Right? Remaining all will be cancelled. Right? So, rho oil, density of the oil equal cross multiply. You will get 4/3 density of water. So, option B is correct one. Concept is which law? It is Archimedes principle. Whenever a body partially or fully immersed in liquid, the weight of the body is equal to weight of the water displaced. That's it. That's the concept. If there were no gravity, which of the following will not be there for a fluid? If there were no gravity, which of the following will not be there for fluid? See, viscosity, that friction will be there. If there is no gravity, which of the following will not be there for fluid, right? So, viscosity definitely will be there. There is a friction, right? And then surface tension also will be. Pressure, sure. So, according to Archimedes principle, we know that Archimedes principle explains the buoyant force does not depend on acceleration due to gravity, right? So the buoyant force depends on acceleration due to gravity. So when there is no gravity, which of the following will not be there for a fluid? But Archimedes principle shows buoyant force depends on G. But here there was no gravity. Which of the following will not be there for fluid mean? Archimedes upward thrust only. Correct answer. Because upthrust depends on G. Here there is no G mean answer D. Right? And the last one, the boat carrying the steel ball is floating on the surface of water in a tank. If the balls are thrown into the tank one by one, how will it affect the level of the water? Right? See that a boat carrying steel ball fully is floating on the surface of water in a tank. A ball are thrown into the tank one by one you are throwing. How it will affect the level of water? Boat carrying the balls, iron ball or steel ball floating on the surface of water in a tank. The balls are thrown out of the tank. See, the balls are thrown into the tank. One by one you are throwing into the tank. So what happens? It will rise. Right? The level will definitely will rise. So that's the end of today's session. Right? So the last one. See here. Correctly look into the problem now. In this problem, yes, one more. Yes. Here, just to check it, the last one. Just the last problem. Yes, here just a correction, make it right. See that two solid ball, one of steel and other is aluminium, which is immersed completely. That is okay. And next problem, see here. Yes, this is also correct. Yes, here you see that when we are throwing into the tank, it will fall, right? Corrected. The level it will fall here. And the last question, a candle of diameter d is floating on a liquid cylindrical. See that the cylindrical container of diameter capital D, the cylinder diameter capital D, candle diameter small d, right? It is burning already. If it is burning at the rate of 2 centimeter per hour, then the top of the candle will, see that is going on burning. A candle diameter small d, it is floating on the liquid of the cylinder. The cylinder diameter is capital D, candle diameter small d. See that D greater than D, right? If it is burning at the rate of 2 centimeter per hour, then the top of the candle, what happens? See the option remains at the same height, fall at the rate of 1 centimeter per hour, fall at the rate of 2 centimeter per hour, go up the rate 1 centimeter per hour, right? Which is the correct option. Since it is burning at the rate of 2 centimeter per hour, it fall at the rate of 1 centimeter per hour is the correct answer, right? Option B is the correct one, right? And that's the end of today's session. We will meet you in the next YouTube class with another important concept. Till then, myself Vetrivel, Unacademy Physics Educator, signing up from you all.